Welcome to another exciting readings class. Where is everybody? All right, so last time we got together informally, I offered 20 extra points for homework number 1 for those individuals who were able to make it to the presentation by Mohammed Avenaki. And I think I recognize many of you were there. Did everybody come? Everybody came, so you got all the 20 points already. It's already appeared on your grades. So that's good, right? That was a nice way to pick up 20 points. All you had to do was show up and sign a thing, and bammo, 20 points. Wow. So that was worth it. Was it a nice presentation? It was okay? I had a lot of difficulty sleeping the night before, but during the presentation, no problem. I don't know what happened. It was are you familiar with the term the PowerPoint death march? So many PowerPoint slides. I just never saw anything like it before. And I stopped and I said, don't you think you should let some time for questions? Oh, yeah. I'll just do another 12 slides. It's like, holy mackerel. So how could you do it? He said, but it was very interesting, and I was very glad that mostly I stayed awake for the whole thing. Mostly. So, next Monday, completely different presentation. And, yes, 20 points will be had. But not homework 1 this time, it'll be homework 2. And I will send out an email to everyone so that you will know. Same exciting time, same exciting place, in the library, in the basement, no windows, no ventilation. And Dr. Radian Ballou will tell us a little bit about microgrids. Microgrids, you may not know, they're a big deal in Germany, because in Germany they gave everybody credits for having solar cells on their roof. And so everybody is running their own power plant. From an electrical engineering point of view, this is an absolute nightmare, because you now have 1 million people generating solar power, and then what happens? The cloud comes overhead, and now you have not enough power for the grid. So now what do? Well, now you've got to fire up the generator. But how can you do this? The generator needs to, light it. How long does it take to boil water? Forever. Why? Because this is not a pot of water that you put on your stove. This is an industrially sized boiler for generating steam power through a turbine. It takes a long time to heat it up and get it up to pressure before you can start to generate the gigawatt you need in order to replace the fact that everybody has cloud cover now. So you need instant start boiling water generation from whatever energy source that you're looking for. And so having microgrids distributed all over the place is very important, because they're all going onto the grid, but they're fairly unreliable. The wind doesn't always blow. The sun doesn't always shine. Everybody is used to having it so that when they turn the switch on, the lights come on. They don't get a message that says, wait a minute. Right? That's not good. So, what do?
When I was living in Maine,
yes?
The way that it worked was you, as a micro entity, you produce all the energy that you need, and you store it on your own batteries.
Batteries.
Whatever you have in your house. And then whatever is extra goes back into the grid for everyone else to use. And you actually get a check from the electrical company going back to you, because they're feeding off of your energy instead of the opposite way.
Well, if you're on the grid, you don't need batteries, because you can use the grid as a battery. And so that's what they're doing, is they're pumping energy back into the grid and getting the power meter to run backwards, and then pocketing the difference. And that's fine for when they're using more than they are able to generate. They suck it down from the grid and it goes forwards. Well, as it happens, that is exactly the kind of situation we're dealing with here with distributed power generation on small grids, microgrids. And so that's what Radian will tell us about. All very interesting. I think the reason why there is value for us to go to these presentations is because we get to see how real professional researchers do research. And so we get to learn what it means to do the kind of research that is recognized for a PhD level task. So that's when we go to these things. It's for our own, I will call it, professional development. But also it's part of the course. We get to learn how to do proper presentations. And I think it behooves you to ask questions. So don't be shy about asking questions when presentations are made. And I think that, I know I asked several questions, maybe more than anyone else, but I sat in front and I'm not shy. So it's okay if I do it, I guess. I notice everybody sits in back. This room is empty. What are you doing back there? You can come forward. It's okay. You don't have to be so far. Anyways, I thought that it would be nice for us to do this. It's a good, it's an interesting presentation. After this one, we'll have another presentation. I believe it'll be Williams, March 12th, which will be the same week, only on Friday. Is that right? Friday the 13th? No, Thursday. Yeah, I don't know why it says this. It'll be on Thursday the 13th, that week. And that will be another homework where you can get you can juice a little 20 points. And this will be on MEMS technology. MEMS. So this person is from Alabama. I don't know if you're familiar. Alabama is south, way south of here. From a big school. University of Alabama is what they call a Research 1 school, big school. And it's a person who's interested in doing ultraviolet lithography. What is lithography? Come on in. Lithography. What does litho mean? Litho. Litho means stone. It's the prefix for stone. Graphy means writing. So lithography literally translates into stone writing. Stone writing because a lithograph, they would take stone and they would carve a design. Then they would take the stone and they would put it in the ink. Then they would take the stone and they would stamp out the paper. That's called lithography. And so when you go to buy a lithograph at the art store that's been printed, it was printed in a printing press that had a lot of pressure, that pushed some sort of a plate onto a piece of paper. And so this is how Gutenberg prints Bibles. This is how people print in a modern printing press. It's how newspapers are printed. Lithography. But optical lithography is different. In optical lithography, what they do is they take a transparency called a mask, and they put it over something which is sensitized, like a wafer. And then they use a step and image scanner, which allows them to have intense optical radiation. Although sometimes it's not visible radiation. Sometimes it's ultraviolet radiation. And sometimes it's deep ultraviolet radiation, which is also known as a soft X-ray. And that's the kind of machine that they use at present, are deep UV machines. These are the ones they build over in Wilton at ASML. So when they do lithography machines for making chips, what they're really doing is optical lithography. And so whenever anybody talks about lithography in the semiconductor world, they're not talking about a stone covered with ink stamping out paper. That's a different kind of lithography. So when somebody says something about UV lithography, they mean ultraviolet. That's optical lithography. When they talk about MEMS, and you'll learn a little bit more about this than, and he knows, he's an expert, so he'll tell you all about it. What does MEMS stand for?
Has to do with semiconductors. I just forget what it stands for.
What is it? I thought you almost said something. Micro? Can you mumble a little louder, please?
I'm not sure.
Oh, okay. You said micro... What?
Yeah. Microelectronic.
Mechanical. Yes, it's microelectronic mechanical systems. So, for example, accelerometers. Accelerometers are fabricated so they're only micrometers across, and when they move, they touch one another, and you can sense that motion. So when you fabricate these things in a plane like this, you can sense motion going like that. When you fabricate them in a plane like this, you can sense motion like that. So what they do is they give you 3 to 6 degrees of freedom worth of motion sensing. They can angle these things, and you can use them for estimating your position and your orientation. That's very good if you're trying to do navigation in a robot that flies. Flying robots include helicopters, airplanes, things like this. Also, if you have something like a personal digital assistant with a touch screen, if you take it and you turn it and then the image turns with you, that's because it has a MEMS device inside. That MEMS device is measuring the acceleration. So that's the only way it can know which side is up when you start moving things like that. So MEMS devices can be fabricated in any one of a number of ways, and he's going to show us how to do it with UV lithography systems. So that's exciting. Yeah, that'll be the 13th. Same exciting time, same exciting place, down in the library in the basement, no windows, no ventilation. 20 points. Maybe the 20 points shouldn't go on homework 3 because a few people got 0. We could add it to homework 4 instead. I'll send an announcement and we'll solidify that. And also CC you on this announcement here so you can see the talk in your inbox. Are there any questions about this? No? Okay. Another one I have coming in from out of town, you saw the Avenaki, is Balaji. Balaji is Uma. She's from Connecticut. And she's going to give us a talk about resonant iris filters. I know nothing about this. Really nothing. So we'll have to figure out what this does and why we want it. It seems like it's eigenmodes and filters. What is this? You guys know what this stuff is? I don't know what it is. Okay, you know what a waveguide is? What's a waveguide? You ever hear of that? Never heard of a waveguide? A waveguide, if you have a wave, which is an electromagnetic phenomenon, and you want to direct it without loss, what you do is you create a resonant cavity that's as wide as the wavelength and as long as you want to use for your transmission. If you are transmitting at power, and by at power I mean many tens of kilowatts, if not more, maybe hundreds of kilowatts, you do not want to just transmit this through some simple wire because it's going to melt. At that frequency, every wire is a transmission line. So for people to get, for example, the output of a power amplifier in UHF frequencies at power up a tower, which could be many hundreds of feet long or tall, you need some sort of a waveguide, right? So for VHF, which is around 100 megahertz, at many tens of kilowatts, they use what's called heliacs. Heliacs has a hollow core and a hollow outside shield, which is solid, and then is pressurized between the core and the shield. And that outside core and inside core are corrugated in order to reduce what's called the surface effect. Electrons don't like one another because opposites attract but likes repel. So the electrons migrate to the outside and create eddy currents. To reduce those eddy currents, they give you an interesting corrugated shape for the outside of your heliax cable. If you want to do this with with UHF instead of VHF, you change the shape of the cable and you make a square channel. That's your waveguide. It looks like pipe, only it's a square pipe. And then the wave can carry substantial power, hundreds of kilowatts at UHF, without much loss, and they can carry it straight up the tower. That's a waveguide. This is what this person does. So this is high power microwave transmissions. So when you think about resonant cavities, when you think about filters at that frequency and power, you're starting to think in terms of transmission lines. I used to be the chief engineer for a radio station. Our radio station output was 10 kilowatts at 100 megahertz. It was 91.5, but 100 megahertz. And so we needed heliacs for transmissions. But for the UHF stations, they use something that kind of looks like a patch bay made with pipe. And the pipe looks like square pipes. And so you take the square pipes out and you mess them around, and that can redirect power amplifier output out through an antenna. So people in electrical engineering really care about that stuff when they start to think in terms of high power transmissions at high frequencies. Because if you have a lot of loss, you're going to pay for it. And the reason why is because if I have an inefficiency in the transmission, that'll just be my power bill being converted to heat. And I don't need that. I'd rather have the power go up the tower and out to the receivers than have it be converted into heat. Where else do we see these kinds of high frequencies? Aside from RF transmissions meant for communication systems. No ideas? How about in our computers? Don't the computers run at gigahertz? That's microwaves. If you have a clock on a CPU motherboard and that clock runs at 2, 3 gigahertz, that wavelength is tiny. That's a tiny little wavelength, right? Because if you think about it, if it was running at 300 megahertz, you'd take 300 million meters per second, and that's the speed of light, divide it into 300 million cycles per second, and you get a wavelength of perhaps a meter, right? If you went to 3 gigahertz, now you have something which is like a tenth of a meter. I mean, it's starting to get out there in terms of the wavelength. So now, if you're thinking in terms of a tenth of a meter, what do they call that? So like 10 centimeters? Something like that, right? Isn't there like 100 centimeters in a meter? You guys came from a metric environment, so you know these things, right? 1,000 millimeters to a meter, right? 100 cent. That's why they call it centimeters, right? Because centi means 100. Isn't that right? So if it's a tenth of a meter, it must be like 10 centimeters, which 2.54 centimeters to the inch means it's a couple or 3 inches. You know, it's that. That's your wavelength. So, you know, if you're thinking in terms of very high frequency stuff, which is what we're finding now in CPU motherboards, you all of a sudden have transformed every printed circuit board trace into a transmission line. And if there's a corner, a sharp corner, that's going to radiate energy all over the place. So now when people design printed circuit boards, they design them so that they have nice curves around the corner because they don't want to create eddy currents that cause radiation patterns. Good stuff. So we should learn about these things by going to this talk. How'd you guys make out with the homework? Easy, right? Ethics? Cake. No questions about the homework? So, just to review, what's utility ethics? Yes, you want to maximize happiness. You want to see if you can maximize happiness of your customers, happiness of your shareholders, maybe happiness of your board of directors, right? Now, I don't know if you remember from last week. I said, isn't it interesting what they call them fracking companies were doing, because they said they didn't want to take their oil tanks and make them safer because it costs too much. Meanwhile, if you've been following the newspapers, they incinerated an entire town. And one of those fracking companies that was transporting oil got sued out of existence and declared bankruptcy, which makes shareholders very unhappy. In addition to, I think they killed 41 people. I mean, it's a really horrendous way to practice your corporate ethics. Do you know what they did? The EPA has no power to regulate the fracking companies. They went to the Department of Transportation, told them what they were doing was unsafe. The transportation said, we're banning all transportation of fracking fluids in these oil tankers until you guys can prove it's safe. They just put a stop to the whole thing. Now, how much does that cost the industry? Before, tankers were too expensive to make safe. Now they're just going to shut the whole thing down. So in the long run, it backfired on them. They had an opportunity to use utility ethics and make their shareholders happy, and maybe make the customers happier by not incinerating your customers. In some circles, incinerating your customers is considered rude, right? You're not supposed to burn people up. It's bad. And so utility ethics, you think that would have applied to these people, but they had no ethic considerations at all. Very short-sighted. And now the whole industry has been punished for it, which I'm very happy to say. I mean, they really should have stepped up to the plate and made life a little bit nicer for people. What was the other kind of ethical consideration they could have made? Say it again? Virtue ethics. Okay, so virtue ethics, you do the right thing because that's the right thing to do. You're reading that, aren't you? That's okay. Oh, okay. I'm very gullible because I have virtue ethics. So let's see. What are the other kinds of ethics? When you follow the rules, right? So you have a code of ethics and you just want to follow that rule of behavior. What do they call that ethics? I don't remember. What kind? The IEEE ethics. Yeah, but is there a kind of... yeah, but I mean, there was virtue ethics, there was... I know it's the IEEE Code of Ethics, but it's not one of the standard ethical... What's it called? What is it? Utility ethics. So when you follow the rules, that's utility ethics too? I wasn't sure about that. That doesn't seem right. We did utility ethics. We did... the ethics where doing the right thing is the right thing to do. But if you're just following the rules, these IEEE Code of Ethics, they had a different kind of ethic model for it. I forgot what it's called. You guys will look it up. Or you want me to look it up? I'll look it up. Let's look it up together. I don't know why I forgot. It was Virtue Ethics, Code of Ethics, Responsibilities. I don't have a good name for it, and I know we had this. It'll come to me in a second. What's it called?
Regulation ethics?
It is a kind of regulation ethics, that's true. Deontological ethics. That's what it is. Deontological ethics. So it's not in here, but it should say it. So these are the deontological. That's when you're following the rules of behavior. Deontological ethics. In fact, I think you can even look that up. I must have forgot to mention it. That's why no one knew it. Deontological ethics. Hey, look at that. Deontological ethics. Normative ethical position, judges morality as an action, adherence to the rules. So I'm not doing it because it's the right thing to do. It's because rules are rules. Rules are rules. It's policy, sir. It's policy. But I can't take that flight because it means getting up the next day and I have no place to go. Sorry, sir. It's policy. Deontological ethics. I don't know if you knew this. Muhammad Avenaki had no way to get home. They canceled his flight out of White Plains. So he had to go out of LaGuardia and travel through rush hour traffic just to be able to make it in time. And I still don't know if he got home. He might still be in the airport. Isn't that terrible? I should call him and make sure he's okay. Not only did they cancel his flight, but in the process of canceling his flight, I called Delta for him. And after Delta starts canceling flights, getting through to customer service is impossible. What's the ethical ramification of that? Running an airline where you cancel flights and then you don't answer the phone? Yeah, they have a monopoly. They don't care. They just don't care about you, the customer. Yeah, does that somehow... You know what they have done? They've treated customer service as an overhead or a cost, instead of as an opportunity to make a lifelong customer, and instead of as a mechanism for improving their relations with their customer, they just said, who cares about you? I'm going to reduce costs by putting insufficient numbers of people there to answer the phone. That's not very good utility ethics, is it? But what are they doing? They're optimizing for cost, or so they think. But in fact, what they're really doing is that they're making themselves out to be a low-quality airline.
Also, the way that they cancel flights, I mean, they take care of their best customers is the way that the airline model is. So if you are a frequent flyer and you fly all the time, you're less likely to get bumped off a flight or your flight.
They canceled the whole plane. Yeah, everybody. Yeah, the people who fly out of White Plains were all disappointed. Plus, they had booked him on a flight automatically without asking him that left the next day. Yeah, so he would have... he just looked at it and said, it's not when I'm leaving. I doubt it. I think they would have told him after he got to the airport that his flight had been canceled, and then he would have said, you can go out of here if you just hang out here in the airport until tomorrow. He was flying out at 6 o'clock in the morning out of White Plains. Imagine coming to the airport expecting to board your flight and finding out it's canceled and being told, well, just hang out till tomorrow. All right, so here comes your next assignment, and it has to do with model validation. Everyone here will find a way to make a thesis proposal that can be validated. And what I'd like to do today is I'd like to tell you a little bit more about what validation is and how you can go about doing validation. How many people have heard of validation? Yes? What does validation mean to you, Mike?
That if you say, it's like proof. If you say 2 plus 2 equals 4, someone else should be able to prove that fact. That would be what validation is.
Okay, very good. So validation means being able to verify something that's been asserted. That's validation. So one thing you can do when you run your thesis is you can collect empirical data. Somebody said they wanted to design a new architecture for computers that would be faster. I said, great, how will you validate your model? You say it's going to be faster, how will we know it? And so, in theory, you'll be able to accumulate some data that will allow you to observe the behavior of your system. You'll have to run some kind of an experiment. You'll have to build something. Someone said they wanted to do healthcare informatics in order to be able to predict the incidence of disease. So then I'm like, well, how are you going to validate your data? You're going to have to be able to gain access to real healthcare data, and that is a challenge. And so as a result, without a good plan for validation, the thesis isn't really feasible. You need to find a way to get the data that's going to help show that your predictions are correct, or else there's no validation. I can't remember any other theses offhand. But if somebody had an idea that they wanted to build a security system that was going to involve cell phones using SMS network, I think that was one of the proposals I saw. Well, maybe that's okay. Your assertion is that you'll be able to make something work properly through the cell phone network. I think you're going to have to build something. I think you're going to have to test it. Maybe you'll test it by using some sensors on the bench. Maybe you won't install it in a house, but at some level there'll be some proof of concept prototype behind the assertion that you can actually build this thing, whatever it is. And maybe it only measures, it's a security system, maybe it only measures when a window is opened. Or maybe it measures the amount of smoke in the room. Or maybe it measures carbon monoxide. Or maybe it can do control. Maybe it can unlock a door. You know, security happens in many forms. It's not just about sensing. So it's somebody who's building a security system is going to have to do a proof of concept prototype. They're going to see certain feature points, right? Those function points or feature points are going to be part of their experiment. What are some of the other proposals? I can't think of them offhand. You guys want to volunteer one? Say it louder, please. Ah, great. Wetricity. So if you have wireless electricity, I'd love to see that work. So presumably your thesis would have an approach that involves building some sort of prototype, and then maybe validation will be testing its ability to transfer power at distance. So maybe it doesn't have to be right on top of the pad. Maybe it can be a little bit further away. Maybe there are ways in which you can make that work with exotic antennas that you plan to construct and test at different frequencies. So that would be a way to get empirical data and validate your results. No one will buy your device until you have a prototype that actually functions. So building something that functions and proving that it functions is so important. So the way I think about it is there's two kinds of empirical analysis that you can arrive at when you go to collect empirical data. One I will call quantitative, and the other I will call qualitative. In quantitative, I measure everything. I get my spreadsheet out, I tell you the average, the standard deviation, I figure out what has happened. But on the other side of the coin, the qualitative analysis is, why does that happen? So if you told me, gee, I'm running a bank and most of the customers peak in terms of their entry into the bank at lunchtime, and I could say, aha, at 9 o'clock I get 10 customers an hour, but at lunchtime I get 100 customers an hour. So that's what happened. That's quantitative analysis. But then if you said to me, geez, I wonder why that happens. You say, well, because nobody has time to go to the bank except during their lunch hour. Aha! That's qualitative analysis. So it's very good if you can get a little insight into what's going on. So it's very important, I think, to do quantitative analysis, to take the measurement, but then having a hypothesis that allows you to draw an abstract conclusion about the data is so important, because otherwise you can't really get any insight into the problem. So let me see if I can come up with some more exotic and interesting examples. I have been trading on the side in the stock market. And one thing I see is the entire market has a pullback because somebody said something bad about Ukraine. And maybe we'll send in troops, and maybe there'll be blood in the streets, and maybe there'll be another war, and the market tanks, and all the stocks go down. But not my stocks. Why? Because they're involved in a massive repurchase. And so that's a qualitative analysis. I could say, aha, I can tell you what happened. They didn't go down when everybody else went down. And the reason why, that's the qualitative part, is because they're involved in a massive stock repurchase program. And that just keeps the stock up artificially, even though probably should be going down soon. So as a result, I can have both what happened and why it happened, both the quantitative and the qualitative. Can you apply this to your research? Would anyone like to take a stab as to how they might do it? I'm going to start calling people. Seems like we don't have many people here. I can call on people. See what I have here is I have a list. Riti? Absent. Tariq? Absent. Anurup? Absent. Sairam? Nobody's here. Vijay? Nobody's here. Sumit? Sai Chandan? Ranjit Kumar? Aha! Somebody's here. Good. Ranjit, how would you apply empirical analysis here to your problem statement? Quickly just tell us what is your problem? Say it again. I didn't catch it.
Autonomous underwater vehicle.
Oh, an autonomous underwater vehicle. Okay. You got to talk a little slower for me. You know, there's a noise that comes from this thing, and it acts like a screen. So what would you do for your quantitative analysis? Are you going to build something? So you're proposing that you actually build an autonomous underwater vehicle? I'm not hearing a yes, and I'm not hearing a no. Are you going to build something? Oh, so you just want to do a navigation system. So your problem isn't really one of autonomous underwater vehicles. Your problem is one of underwater vehicle navigation. So are you going to build a navigation system? Okay, great. So your navigation system will give you a proof of concept prototype, right? Yeah, so after you build your proof of concept prototype, you're going to measure its behavior. And it'll tell you how precise your prototype for navigation is, which is a very fine thing. Maybe you'll use MEMS devices because they'll be underwater and you'll be measuring acceleration. And then that measurement will probably have some error, and for qualitative explanation for the error, you should be able to tell us why there's this error. Maybe even how you could get the error a little bit better, improve the error. So you're constructing a real gizmo, a real gadget. So that is, I call that both quantitative and qualitative. Arun, yes, tell me again what your thesis problem is.
It's controlling a fast by using SMS.
SMS. And what did you want to control again?
The power strip.
Oh, a power strip. Right. Okay, so that's definitely a gadget. You can build that. When you see it running properly, that's quantitative. If it takes a little while before the message you send actually turns something on or off, you might be able to tell us why. So if there's latency because of something that has to do with how long it takes a message to go to the cell tower and then come down to the power strip, and there almost always is latency, but there may be a big variation on that latency, you should be able to explain why that happens. And then that's qualitative analysis, right? So as I see it, SMS has some, I'll call it, intrinsic limitations in terms of the quality of service that it can provide, because messages don't come through right away. Messages always take time. Good. So then there's this thing called modeling. How many people here have ever tried building a model? Yes, one person only? What kind of model did you build?
Model cars.
Oh, model cars. Yes, yes, yes. Well, model is an interesting term. It can have many different meanings. A model car could be a replica of some car that is made to a scale. So the model car that you play with as a toy is perhaps done at some large scale, like at 1/20th size over the real car. But let's assume that what you're looking to do is model via simulation. So what you're attempting to do when you model via simulation is you're attempting to replicate what occurs given a set of input data and output data. So when certain things happen, other things are caused. And the model enables you to simulate the input-output relationship. So if you have what I call a system and you want to reproduce the behavior of the system, it would be really good if in the real world you had empirical data which gave you both input-output relationships. For example, when I fill up my bathtub with water, the floor gets wet. Now I could try and model the container that is the bathtub using something like, I don't know, a 1/20th size bathtub, my coffee mug, and then I could try and fill it, and the abstraction indicates, according to the model, there will be overflow and it goes all over everything. So this is the model, right? It's not really the bathtub, it's just a little bathtub. Right? It's simulating the bathtub. So I can make some prediction about what will happen. Every time I fill up the bathtub, the floor gets wet. That's predictive. Now let's assume I want to fill up the bathtub just enough so that the floor doesn't get wet. That's a control system, right? So that's what's known as prescriptive. You could do the same thing with a humidifier. If I fill up the humidifier too much and then the air handler gets all wet, then it all gets rusty and all the motors are ruined. It's terrible. But if I fill up the air handler just enough so that maybe the filter gets wet and then I can circulate air through and it gets humidified, but I don't get everything else inside of the air handler wet, that's prescriptive. So predictive means you're trying to make some sort of simulation that predicts the reality or the real world. Prescriptive means you're trying to do control. It means you're trying to use your model in order to be able to obtain some sort of a well-regulated outcome. I'll give you an example. Suppose I have a model for this room and it involves heat. The room is filled with air and the air has a specific heat capacity. I have a sensor which I call a thermostat. I should have a thermostat. I don't have a thermostat. Oh. So presumably there's a thermostat in the corner, and somebody somewhere down in Heating Central measures when the room is cold and then turns on the heat. So they are attempting to use their model of the room in order to be able to raise the temperature. So one could make a compelling argument that if they let the heat go for too long, the room will get too hot, even before the thermometer over here catches up and starts to measure the change in temperature. So their model enables what is called prescriptive change, right? So it's model-based control. So model-based control systems generally have a real-world item, which we call the plant. They have the model-based item, and then that gives us a link between the plant, which is the thing we're attempting to model, and the model itself, and that link is usually a sensor or a sensor network. So the sensors give us feedback from the plant and allow us to adjust the model estimate for what the plant is doing. And the plant could be this room and its heat. It could be a robot and where the robot is on the room. And maybe the sensor isn't a thermostat, maybe the sensor is an ultrasonic thing or a camera or a MEMS device that gives us acceleration, or even odometry. And what we'll do is we'll take the sensor input and we'll use it to fuse our idea of where the room is. And we have a model for how, let's say, the car will move. And cars are interesting because sometimes they have front wheels and they have back wheels. And usually you can move a car anywhere on the plane, but not any way you like. Because most cars are not like chairs that can move in any direction. They don't have casters. Most cars have front wheels which have to have a front wheel angle. And you have to steer into the car and maneuver in different directions in order to be able to get the car in the orientation and position that you're looking for. That model of the car is completely different than the model for this chair. Right? And by using front wheel angle and odometry, plus an accelerometer and maybe even an ultrasonic sensor, I can model the car and update that model's estimate for where the car is in the plane so that I can properly position the car. So if we think about it, that gives us a model-based control system so that we can get the car into a specific place at a specific orientation. That is, we can use a control or prescriptive model for the car in order to maneuver it into a space. What do you think of that? So who hasn't gone yet? Durga. Is Durga here? Absent. Uday. Also absent. I'm missing so many people. Deepak. Yes, Deepak. So tell us again, what is your problem statement? Microgrids. Oh, this is going to be a great talk for you. Right? Because you're doing microgrid. Wow. That's terrific. What problem in microgrids are you going to attempt to solve? Power storage in microgrids. Okay. Are you going to model something, or are you going to build something real? Are you going to build a model? Okay. So you'll have a model of a storage system. Let's say it'll be a rechargeable battery, maybe. Okay. And then is there some what is the battery going to model? Is it going to model some bigger battery?
Yes, it's a bigger battery.
Okay, so you'll build a little battery to model the bigger battery. That's good. So you're going to simulate this bigger battery with your little battery. Presumably you're going to predict how the bigger battery works, and maybe you'll control the amount of charge that it has. Certain things about batteries are important, such as the rate at which they are charged, but also the total amount that they're discharged. If you discharge the battery too much, then it'll never recharge again, not fully. So you can damage a battery by fully discharging it if it's a certain kind of battery. LiPo batteries. You don't discharge LiPo batteries, lithium polymer batteries, completely. You discharge them a fraction, and then you recharge them. As opposed to NiCad batteries, you should discharge those almost all the way, and then you can recharge them because they have memory effect. So it depends on the chemistry of the battery. Tesla batteries are LiPo batteries. Laptop batteries are LiPo batteries. So when we think about validation, we're going to have a separate section in the thesis, and you're going to focus in on how you will do the validation for your thesis. Who doesn't know how to do validation for their thesis now? Who's confused by this idea? You are? Yes. Okay. What is it that confused you about the talk? Or tell me again your problem. I'm sorry, I forgot. Yeah. So wireless charging. You're going to build something, right? So you want to grab onto energy that just happens to be here. You're kind of doing a passive wireless charging. So you have a hypothesis that energy is available. That's your theory. Right? It's all around. Oh, it could be light. So then solar. So you got solar, you got thermal, you got radio waves, you got vibration. Yeah, you know that I'll call it low power energy harvesting. Well, the trouble is that certain areas will give you better energy than others depending on where you're at. So if you're in a helicopter, harvesting energy from vibration is really good. But if you're just sitting around on the beach, harvesting energy from vibration is no good. But maybe you could harvest energy from the sun. So the question of whether or not you want to have all of those things as an input. So you want to have everything. You want to have RF energy too? See, if you could just focus on one of those things, your problem would be a little easier. Energy power harvesting kits are available, and I happen to have one. And they will give you multiple inputs. The question of whether or not you'll be able to make good use of all three is another matter. I don't know what your vibration source will be, for example. So it's a tough problem. You can use heat, as a place to get energy. They give you thermoelectric generators. So if you had an engine, like with an exhaust, you could use the change in heat to get good energy. They use Peltier junctions for that. Is it time for people to leave for their next class? All right, so why don't we do this? We'll take a little break. And we'll think a little bit more about